Hi guys, my name is Rahul Bish, and in this video I'm going to tell you about the future of VLSI technology. As we all know, the historical growth of IC computing power has profoundly changed the way we create, process, communicate and store information. The engine of this phenomenal growth is the ability to shrink transistor dimensions every few years. Remember, when cell phone looked like this, we could call, text and having a 6 megabyte of memory, which was actually a small miracle at the time. After that, cell phones got faster and faster, slimmer and slimmer, and probably we upgrade our phone in every couple of years. And this incremental technological progress we all have participating in for years hinges on one key trend, Moore's law. This law has continued for the past 50 years. The predicted demise of Moore's law has been repeatedly proven wrong, thanks to the technological breakthroughs. For example, optical resolution enhancement techniques, high-k metal gates, multi-gate transistors, fully depleted ultra-thin body technology, and 3D wafer stacking. However, it is projected that in 1 or 2 decades, transistor dimension will reach a point where it will become uneconomical to shrink them any further, which will eventually result in the end of CMOS scaling roadmap. So now, you guys are thinking, what after CMOS? So let's discuss some potential post-CMOS candidates. Number 1. Steep transistors. The ability to shrink a transistor supply voltage is determined by the minimum voltage required to switch the device between an on and an off state. The subthreshold slope is a measure used to indicate this property. For instance, a smaller SS means the transistor can be turned on using a smaller supply voltage while meeting the same off current. For MOSFETs, the SS has to be greater than this value. Here SS means the subthreshold slope. This fundamental constraint arises from the thermoionic nature of the MOSFET conduction mechanism. Many device types have been proposed that could produce steep SS values, including tunneling field effect transistors, nano-electromechanical system, ferroelectric gate, and impact ionization MOSFETs. These so-called steep devices' main limitation are their low mobility, asymmetric drive current, and larger statical variation in comparison to traditional MOSFETs. Number 2. Spin devices. Spintronics is the technology that utilizes nanomagnet spin direction as the state variable. Spintronics has unique properties over CMOS, including non-volatility, lower device count, and the potential for non-Boolean computing architectures. Spintronic devices' non-volatility enables instant processor wake up and power down. That could dramatically reduce the state power consumption. These devices could potentially overcome the power bottleneck of the CMOS scaling by offering a completely new computing paradigm. In recent years, progress has been made toward the demonstration of various post-CMOS spintronic devices, including all-spin logic, spin wave devices, domain wall magnets for logic applications, and spin transfer torque magnetoresistive RAM STT-MRAM and spin Hall torque SHT-MRAM for memory applications. Number 3. Flexible electronics. Distributed large area electronic systems based on the flexible thin film transistor technology are drawing much attention due to the unique properties such as mechanical conformability, low temperature processability, large area coverage, and low fabrication cost. Various forms of feasible TFTs can either enable us applications that were not achievable using traditional silicon-based technology or surpass them in terms of cost per area. Flexible electronics cannot match the performance of the silicon-based ICs due to the low carrier mobility. Instead, this technology is meant to complement them by enabling distributed sensor systems over a larger area with moderate performance. Development of inkjet or roll-to-roll printing techniques for feasible TFTs is underway for low-cost manufacturing, making product-level implementation feasible. Despite these encouraging new developments, the low mobility and high sensitivity to processing parameters present major fabrication challenges for realizing flexible electronic system. CMOS scaling is coming to an end, but no single technology has emerged as a clear successor to silicon. The urgent need for post-CMOS alternative will continue to drive high-risk, high-payoff research on novel device technologies. Replicating silicon's success might sound like a pipe dream, but with the world's best and brightest mind at work, we have reasons to be optimistic. Hope you guys have enjoyed this video. Thank you.